Right. So in this case, it will take by time. In this case, it will take by minus t. The difference is pi minus pi, which is 2 pi. So that's why this so you will always there's no backscattering because it's a
it's already going.
Well, thank you all very much. In particular, thanks to the organizers of this meeting for asking me the comments. So the work that I will be discussing today was by a great deal inspired by experimental colleagues that I had in Ames and at the Ames laboratory, which is currently in a deep freeze. So it's very nice to actually be here. I have a large list of experimental and theoretical collaborators on this problem. This is your point. Yeah. And the ones that are listed in red are the ones that specifically contributed to the work that I will be discussing today. There is Rafael Fernandez, who is a postdoc working with me in Ames. Premi Chandra, who is here in the audience. Paul Canfield, who supplied lots of these samples. Work was done. Alan Goldman, who did X-ray. Andreas Kreisig, X-ray. Rob McQueenie, neutron scattering experiment that I will be presenting. And there's also elastic constant measurements done by Willie Kaplan on samples by David Mandras. And well, the talk is about frontiers in quantum matter. So if you look into what happened, in some cases inspired by, for example, Coupe superconductors or other correlated materials, we've learned a lot about interesting states, interesting phenomena, that have captured our activity and our creativity for a number of years, such as quantum criticality here in an insulator, or in metallic heavy fermion systems, or starting with helium-3 and leading up to the cuprates, the organics, the heavy fermions, unconventional pairing states. We've also had a number of interesting theoretical developments. Here's one given by our previous speaker in the context of cuprate superconductivity, where we can combine order parameter symmetries of a superconductor and of a magnet. Or here I'm listing some very, very nice work on frustrated spin system done by Premi Chandra, Piers Coleman, and Anatoly Larkin. And wouldn't it be nice to have a system where all of those would be realized? And then I argue that the new iron nictide superconductors are in fact a beautiful example where a number of very, very exciting and interesting concepts can be found and can be studied in quite some pristine detail. The paper, as many of you know, but maybe some don't, is a 2008 January publication in the Journal of the American Chemical Society. I will mention it right away in it. As of Thursday, I think it had about 1,000 publications, so it's a reasonably well developing field. Just to remind ourselves, the initial material in this family is a lanthanum, oxygen, iron arsenide system that has a superconducting transition temperature of 26 Kelvin in the mentioned publication. Superconductivity was found by substitution of oxygen by fluorine, and this material can be rationalized as being coordinated copper, iron, and with arsenic up and below these layers separated by lanthanum oxygen layers. This was not just an accidental discovery, but in fact the same group around Hideo Sono had already worked on related systems such as the material where arsenic is replaced by phosphorus, which has a modest TC, and I think they just found the right way to design this to make a large superconducting transition temperature possible by just playing with the chemistry here. Quite a frenzy of excitement came also from Beijing and Defy, where a number of very, very active groups pushed by improving the materials, the transition temperature to larger values, and they're still very active. This is simply when all this started. And finally, there's a noteworthy development in the group of Dirk Jorens in Munich, where another class of material, albeit with a lower transition temperature, was introduced. It's the so-called 1 to 2 member of the family of the materials, and here we have barium iron to arsenate, so the same iron arsenide layers, but it is a material that is not only without copper, but it's also a material without oxygen. So it is truly not a transition metal oxide. And it has the appeal of being easier to control and, for example, grow single crystals. If I list you a couple of phase diagrams, what we see is we have magnetism and superconductivity nearby. This is why this talk is called competing phases, and I will go into quite some detail what I mean by that and what conclusion can be drawn from it. And we have also, as I mentioned, as you can see here, and also here, structural phase transition that is surprisingly close to the electromagnetic ordering transition. This is a transition from a tetragonal phase to an orthorhombic phase, so the four-fold coordinated square geometry breaks its symmetry in one direction, has a shorter one than the other. Let's look at two members of those families and let's look closer to what happens when magnetism meets superconductivity. As one, and for my taste, the best studied systems are those cobalt-doped iron, 1 to 2 materials, and that's simply because it seems to be the materials are very well under control. And in those systems we find that there is a region of homogeneous coexistence. It's actually not a quite correct way to phrase it. It's not a phase coexistence. There's one phase that has simultaneously a finite magnetic and a finite superconducting order. So just the point that there are it's not that we have 4 phases meeting at a point that would violate Higgs phase rule. It's just one phase. But here we have, in other situations, also the possibility that we have a first-order transition that seems to be separating these 2 phases. Now, one might, at first glance, think that this is not particularly universal behavior, but in fact, I argue this is actually an important clue. And to do this, we do something that is in the spirit of the last century, right? As we've just learned, we do a Ginzburg-Landau expansion of a magnetic and an open superconducting order graph. And of course they compete. The question is not whether they compete, the question is to what degree they do so. And this can be just characterized by the leading term that has both order parameters simultaneously occurring as a coefficient. And that coefficient is either larger or smaller than a certain value. And I just characterize it here with some number that is either positive or negative by that method. But in all both cases, these are competing terms. And if this competition is too strong, they will just build a brick wall. They just wouldn't want to be appearing at the same time, and then we have first order phase transition terminated at a bicrystal point. We have here, say, the magnetic, or here the magnetic, and here the superconducting transition temperature, or they can simply cross, maybe change the slope. But important is that there is a region where both orders can simultaneously occur. Again, on the Ginzburg-Landau level, it's just determined by the sign of a number. Good. And of course, the statistical mechanics that underlies this has long been studied. Understood. The magnetic structure, just to remind us, is also quite interesting. I get back to those Ginzburg-Landau expansions in a minute, but I need to talk a little bit of the material. We have a magnetic order that can be nicely characterized as being 2 interpenetrating nailed ordered states. So I have here indicated in blue and in red an up, down, up, down, up, down pattern in both cases, but it's actually interpenetrating. I get back to that too. It has been clearly identified in scattering a number of systems. But we have states in advanced structure calculation that in many cases can be very nicely characterized as having a set of family sheets around one, let's say the center of the Brownian zone, and shifted, in fact, by just the magnetic ordering vector. And in order to get some insight into how the 2 phases compete, I will first of all develop a very trivial and rather simple toy model to characterize, where I just say, okay, I have two sheets, I have a pole and an electron band, and they're just separated relative to one another by the magnetic order. This is not an entirely unrealistic way to think about it. Here are angular result total emission data by Adam Kaminsky in Ames, where we see this more spherically looking and then the more elliptically shaped sheets of the Fermi surface here now moved on top of each other. And upon changing the cobalt concentration, what we do is we seem to be shifting the Fermi level in just a way that one shrinks and the other one gets larger, as you see when you go from here to here. Magnetism seems to disappear right when these two Fermi surface sheets don't touch one another any longer. Also, Hong Ding, who's in the audience, has done wonderful photo emission studies early on, showing that superconductivity seems to be fully gapped in these systems. And this is an observation for one given momentum point in the z direction, so it could still be nodal states in the system, but at least there's no indication that photo emission seems to see nodes of the surfaces. Well, we want these electrons to interact, and for example, if you just look at the low energy states of these two bands, you can, and this was done here by Andrei Chubukov, Ima Yefremov, and Ilya Erevin, you can introduce the various different coupling constants. They are creatively called U1 to U5, so there are 5 of them. For me, what is really important here is, at first glance, and I'll come back to this in more general later, is that essentially certain combinations out of them give us certain ordered states if we look at this from a mean field perspective. Magnetism is being given by certain interband couplings. Superconductivity, again by others, where we have, say, a pair of states here propagating into another band. And this is clearly a low energy model. We don't really know where these numbers come from. It could, for example, be that we have an electron-phonon interaction that gives us a certain, say, attractive interaction for the superconducting channel, and then gives us conventional superconductivity. It could also be that the interactions are more electronic in origin, and if they do so, you can convince yourself that this would imply that this interaction here takes a different sign. So, to some degree, the sign of the underlying mechanism has impact on what the signs of certain interactions are. And the implications for that are pretty straightforward. That have to do how the Cooper pair wave function looks like in the system. If indeed this would be, I call it phonon interaction, so an interaction that has an attractive pairing interaction in the conventional sense, then we would find that these two different sheets of the Fermi surface would indeed find an in-phase, same sign amplitude, and would essentially look like this. Would be a fully gapped state, for example, and this fully gapped state would have a superconducting gap that has the same sign on both sheets. And it was proposed early on in this field that there's another option, namely that as a result of a formally repulsive interaction, a bound state can be formed where they are out of phase, where they have a relative minus sign. So if you wish, you could just write down the wave function on each sheet, and there's a relative phase into 0 or pi in both cases. Come back to what that means and why this is a useful way to think about it. Now the problem is that this state here, it's called S plus minus state, and the S has a meaning. It means there's really no different symmetry problem compared to the S plus plus state, which is in distinction to the D wave superconducting state in the Cooperates, at least if they are tetragonal, where we really can make an experiment such as the corner junction experiment that tests the symmetry macroscopically. Here, this is not quite as straightforward, and therefore it would be interesting to have some other clue as to what is the underlying mechanism here. And as I said, let's talk about coexistence and competition of spaces. So let's see how the superconducting state, and if we focus on these two candidates for the moment, how they would communicate and compete potentially with magnetism. And here are the experimental data that motivated me to get involved, because they're quite beautiful. This is the cobalt-doped iron arsenide system, the 1, 2, 2 materials. Here we have the antiferromagnetic phase, here we have superconductivity. We're looking at the magnetic order parameter, the antiferromagnetic order parameter as we decrease temperature, which of course all arrives here when we are somewhere here, low cobalt doping. And it gets very interesting in the systems where we have a low temperature superconducting state. When the system is cooled down in the magnetically ordered state and reaches the superconducting transition temperature, then the magnetic ordering is being reduced. It goes so far as that this magnetic ordering can even, and this was in fact predicted and then later on found by our colleagues, you can have a system that becomes magnetic right here. And then you go into the superconducting phase, and the magnetic order disappears altogether, and you reappear into the non-magnetically ordered phase. So magnetism and superconductivity obviously are competing here. That's visible, very obvious in the suppression of the order parameter. I've never seen such a strong suppression. The 115 materials, another system where we have two phases of similar kind of systems, sometimes have a saturation of the magnetic order as you go into the superconducting state, but such a strong suppression I had never seen. So why is this interesting? Well, I just told you there are two options. Either you have this second order or first order bordering between two transitions. Now, if I had, and this is obviously coexistence here, but both things do coexist. If you're on one side of the sine composition, we're on this side, where we have coexistence regime, simultaneous ordering, if you wish. If we were on the first order regime, what would happen is that the magnetic order parameter would drop to 0, in fact, in the superconducting phase, because these two phases really don't coexist. And this is, in my view, nothing else but the precursor of being close to a situation where you're about to be first order. So those data show you without any microscopic modeling already that the underlying Higgs-Boson coefficient has to be close to the borderline between these two regimes. Just by looking at this curve, you know that. It's just not negotiable. And any microscopic mechanism will have to, or theory, will have to accommodate this naturally. There's, to some extent, a fine-tuning of a number, as you can see here in the phase diagram of the system.
I have a
Yes.
question. So, can you rule out the possibility of this separation in the
Right. Yeah. For example, well, let me answer this first and then I comment. There's NR done by two groups and mu's are done. So you will have to have a local probe. And for the cobalt-doped materials discussed here, all three experiments agree that we do not have phase separation. We have macroscopically large regions of one ordered state and the other in the system, but in fact we have homogeneous coexistence of both order parameters everywhere in the sample. There are other materials, such as the potassium-doped 1, 2, 2 materials, for example, where the opposite has been seen, where you do see phase separation into macroscopic large regions. Right? And as I mentioned earlier, there are these 1, 1, 1, 1 platinum based 1-1-1 systems where you also have a first order transition and you actually have a regional coexistence. This system here is established to have a homogeneous, simultaneous order. Good. So we are, what we did is we just took this little toy model first. I told you two bands, you have interactions, and you try to just get T-nail right here and the TC value here. And what you find is that for the conventional pairing, you get always a first order line, and the magnetic order parameter immediately drops to 0. While for the unconventional, or the S plus minus pairing, we have a region of coexistence, but yet we have the suppression of the order parameter, even with the reentrance. In fact, this data was taken before, or this calculation was done before the data were taken. So, this is a nice calculation, but it would be even nicer if one could understand why this is the result and what is underlying here. And to do this, I will simplify the model simply for the purpose of getting a deeper understanding and say, well, let's just assume we had a perfect so-called particle-hole symmetry between these two branches. So this branch, the blue branch, is just the whole branch flipped upside down and moved. And then we consider this multi-critical point. Exactly the point where the decision is being made of how these two phases communicate with one another. And whether this is a first order line or a splitting of two second order lines coming at lower temperatures. And then you can calculate the coefficient of the Landau theory. And you find something quite remarkable, that this little toy model, indeed, for the unconventional pairing, has here a coefficient. This is my earlier object that was positive for the second order, negative for the first order, maybe the other way around. Positive for first order, negative for second order, is now exactly 0. This is a fine-tuning simply because we have this particle hole symmetry assumed in addition. But what we do find is that the unconventional pairing indeed is a state where the superconducting order parameter can optimally adapt of all the states we could find for this system to the underlying magnetic state. In fact, when you drop this term, what you see is it doesn't really matter whether you change the direction of your magnetic order parameter or of the superconducting order parameter, just exactly along the line that was proposed with the SO5 symmetry for the Coupons. Here we have at least a toy model where this is an exact realized symmetry. In distinction, if we have the conventional error, with a strong, in fact of order 1, coefficient here, and we are always in the regime where we have very strong first order transitions between both phases. But the reason for that is that underlying is that an S++ state will, in the ordered space, induce nodes of the superconducting gap. Something that was recently also discussed by Igor Mazin and Andrei Chubukov and collaborators. So if you want to look at this, we have here our kind of parameter that decides whether we have a coexistence of first order, and at least from particle load symmetry, we know we're exactly at this limit, and then we can, for example, deform those bands to make them a little bit more realistic, and then you can find that both options are possible indeed. You can find systems that are coexisting, or systems that are having a first order border. And this could well be the explanation of why different systems behave differently. But what's most important here, and this theory cannot predict where a given material is located, and for this you need to have a much more detailed material-specific calculation. Yet what we can say is, if you do find one system that has phase coexistence, then you can exclude that the system is in the conventionally ordered state. Because this object here moves always around its relative, always stays deep in the first order regime. And we have spent quite some time to look into this. So what I say is that just the mere observation of phase coexistence tells us that the pairing of these systems is unconventional in its nature. So again, why does this work? Well, because there is indeed now a wonderful example for this SO5 symmetry. And one can even go a step further. One can show exactly this was done recently by Daniel Podolsky, He and Youngback Kim. If you take this most general model for this two-band situation and you fine-tune the coupling constant in a very, very specific way, that you then find that in fact the order parameter symmetry is not just the SO5, but in fact an even larger one that's also an orbital bond current that is degenerate. In addition to the anti-ferromagnetic and the superconducting state. Well, being at this multi-critical point is exactly corresponds to this fine-tuning of those numbers. Now, therefore, looking at the multi-critical point does indeed tell you something about how these states communicate with one another. And finally, Chubukov and collaborators did a wonderful recoupling renormalization group calculation and find that there's a fixed point in that model. And one would not be surprised that given now that we know that there's symmetry, that there must be a fixed point. It's an attractive fixed point. So at least at intermediate lengths here, this is where the system is supposed to flow to. So we have a good understanding, I think, about the system. All of this is, of course, only a fixed point if we do have S plus minus unconventional pairing. Good. So I mentioned earlier, one can think about it as a phase. So how can we get phase-sensitive information about or the superconducting states, the relative phase between two Hooker pairs in the same material. Well, ordinarily what we want to do if we want to find out what the superconducting state is, we do a junction experiment, a Josephson type of experiment, in order to gain phase information. This is problematic here, as I mentioned, because the symmetries are the same as one of conventional pairing states. But what we want is, of course, the Josephson experiment meets states on one sheet of a family surface with another sheet of the family surface. Well, that's precisely supplied by us, and the matrix element is given us by the magnetic order parameter. It gives us the momentum to couple these two states, because it just provides the necessary momentum. We have a Hooker pair on one sheet, we couple into the other one, we get into the other family surface sheet, and it's sensitive to the phase, and it's exactly this sign that determines, in one case, to be at the borderline between two first and second order transitions, or deep in the first order nature. So, so far about competition between magnetic order and superconductivity. One can now look further and say that the system has other broken symmetries, such as structural ones, and which are suspiciously close to the magnetic long-range order that we see here. And, well, given that the neutron scattering experiments showed those reagent of the magnetic order parameter, it was natural to ask what happens to the structural order parameter in the system, because they're so close to one another. Somehow they communicate. Why would these transition temperatures track one another so nicely otherwise? Here is an X-ray experiment where we see the tetragonal phase as one peak. We go into the structurally distorted orthorhombic phase, where we have two different bond lengths, which is basically the splitting of the peak because we have multiple twins in the system. And now the system is cooled down below the superconducting transition temperature, and we recover one peak again. So the tetragonal phase has a reentrance, just like the paramagnetic phases. And we can look at this more carefully here. And once again, that's the structural order parameter. Structural order parameter rises, of course, and once we hit the superconducting transition temperature, it dies down. Same here, even with a reentrance of the tetragonal phase. This is now structural. So what you may ask is, well, do we have to now again find another underlying symmetry principle that drives everything and fine-tunes the coupling constant in the system? By the way, this would be, in both cases now we have this backbending of the phase diagram. And we have, if you want, the two different quantum critical points here. These are both second order phase transitions, right? So the question is, are we having now another coupling term that couples the tetragonal distortion and the superconducting order parameter? Again, there is a number that takes a certain value just in order to be so close to the first order line. And this sounded rather artificial as a concept because we couldn't see how these two states actually compete similarly strong as magnetism would compete with superconductivity. The answer lies in the fact that there's no competition, in fact, between the structure and superconductivity. The answer lies in the fact that the magnetic structure is frustrated one, something that was pointed out by Tena Yildirim and Chino C. and Ilya Abrams early on. When we look at these two penetrating magnetic lattices, it turns out that this is a well-known lattice in the quantum spin model family, so-called J1, J2 model, and the spin in the middle really doesn't really know how to orient itself relative to those four spins because, at least on the classical level, they all cancel on the central side here. So therefore, the coupling between these two sublattices is not the typically leading one, but they're actually higher order couplings that only there are fluctuations or gradients that go beyond the classical order state. So this is indeed an interesting frustrating state. Problem was studied by these three authors here, and in the context of Nicklight also studied here. So what is interesting now about this lattice? If you look at these two sublattices, it turns out that there's a new degree of freedom, something that was pointed out in this paper by Chandra, Coleman, and Larkin, that the relative orientation of these two sublattices by itself is a new order parameter. 5 minutes. I should stop now.
No.
I can.
5 minutes before question.
5 minutes before. Good. That should be no problem. These two magnetic order parameters have a relative orientation to one another. And in fact, it is possible to have ordered states where only the relative orientation is ordered while the magnetic order parameter is completely zero. Or there are situations, such as in 2 dimensions, where the magnetic order parameter is continuous symmetries couldn't be broken. Or we could also have a situation where we have initially only the relative orientation between 2 order parameters locked before the magnetic order sets in. This gives a very natural interpretation for what is observed in the tektites, as was pointed out in a number of papers, simply because if the relative orientation is so that we have parallel bonds or anti-parallel bonds, well, then the bond lengths will naturally respond to that and will either be larger or stronger. So this order parameter couples bilinearly to the structure, and therefore will induce a structural distortion. So in other words, it is not that there would be a structural transition if it wasn't for the magnetic frustration in the system. Good. So all what we did was to combine the just presented theory for the competition between magnetism and superconductivity. Because ultimately, what it says here is structure is nothing but a collective magnetic degree of freedom. With this work for treatment of this emergent order parameter that says something about the relative orientation, and you can very easily see that the structural order parameter at the superconducting transition temperature can be reduced. You can even drive it to zero. By that token, the competition between magnetism and superconductivity is the primary one, is one on the level of the electrons involved. But the fact that the structure at the same time gives us a very similar suppression of the order parameters, in fact a completely different phenomenon in my view, and it's simply because structure is being enforced by magnetic correlations or magnetic order in the system. So we do not need to invoke an additional fine-tuned coupling constant with another order parameter. It very naturally follows. Maybe one last remark before I'm finishing. If you look at even in the system where you don't have long-range structural order, you still have, of course, elastic fluctuations. And since not only the structural order and magnetic relative orientation of sublattices are correlated, but also elastic fluctuations and, in fact, the fluctuations of this emergent order parameter are tied to one another. You can measure, if you make an elastic experiment, the susceptibility of this emergent pneumatic order parameter, which is something that's otherwise rather elusive to direct measurements. And indeed, these are resonant ultrasound measurements here by Willy Kepler and the collaborators. Here we see the suppression of the elastic modulus, and the solid lines are just theories for this J1, J2 type models, close to but not at structural transition. So suppression of softening of the lattice is nothing but a divergent pneumatic susceptibility. The fact that we see this in such a large temperature regime says that we do have, in addition to magnetic degrees of freedom, important elastic or pneumatic degrees of freedom as low energy soft modes in the system, which, well, may or may not have something to do with superconductivity on its own right. So what do we have? We have magnetism and superconductivity competing strongly, but just in such a way that they can still accommodate one another. And this tells us that we do have, in my view, firmly established that this is an electronic mechanism. There's frustration in the system that tells us something, how magnetism can drive elastic deformations without necessarily evoking a coupling, direct coupling between the structural degrees of freedom and the electrons in the system. Thank you very much.
So one way back then when I thought about SO5, I always thought a smoking gun for it is if you really can identify such a multi-critical point.
Yeah.
Actually to measure the multi-critical exponent. Do you think it would be possible in this?
I think it's possible. These materials.
So there could be a smoking gun for.
Yes, I've told them just that.
Oh, that would be great.
Yeah, I think there's real hope to do that. You do this right.
Well, okay.
Okay. Okay. In this H positive minus,
Yes.
in some way it's similar to D-wave in response to fluid. So for this, the cobalt substitute sample, cobalt substitute lines is your plane.
Yes.
But why the TC is so robust if it's H plus minus? How to understand?
Right. I have no good answer to this, but the only comment I have is historical. I think the key argument against D-wave superconductivity in group waves was for many years it couldn't possibly be because these are so durable materials. So here we are.
No, another question along those lines is that, so why do you say, I can understand your argument why it's less common, but I don't understand your argument why it's unconventional. And I don't see why S plus S minus is so susceptible to any kind of disorder, because it really is conventional. It's really, it has the same symmetry as an underlying lattice. So
it really depends what we call conventional and unconventional. If we say unconventional superconductivity is a state where we break the irreducible representation of the point group, then YBCO is a conventional superconductor. Because D-wave superconductivity and S-wave superconductivity are the same irreducible symmetry. They are the same. They are. That's your. My
the
personal.
lattice and the order pair are different symmetry.
Yeah. YBCO has not a different symmetry than the S-wave, simply because it's an orthorhombic system. It's a bit. No, I'm sorry, it's a symmetry statement, right? And it's either true or not. But I believe that for me, what is unconventional is whether the mechanism that drives the system is electronic or phononic. That's my personal definition, and everybody's free to do their own.
Yeah, question.
So with respect to the neutron standard data, you reduce order elements functions.
Yeah.
Did the local probes show a homogeneous reduction in that local moment?
Local probes have not seen the reduction of the order parameter.
I'm sorry.
Local probes have not seen the reduction of the order parameter of the superconducting state.
Okay. But in the light materials,
Yeah.
on that graph of the order parameter, the n squares, or not squares, did the local probes show that that's homogeneous in order space, like NMR and USR?
Yes.
They do? Okay.
Yeah.
Thank you.
I have a question. What's your real space orbital picture of S plus S minus pairing? I understand in momentum space, what does it look like in real space? And how much will it think of it? For example, D-wave pairing and group rates is very easy to have a real space picture in terms of the copper bond. Is there an equivalent kind of picture for S plus S minus pairing?
Well, you always have to have in each direction two different objects that are allowed to move because there's more degrees of freedom per unit cell. So momentum doesn't classify the system entirely. So you need to have waves that move in different. You have to per real space point another flavor of units, and it is their coupling. So I don't think it's particularly clear.
Any other questions before we go on to the next set of talks? Okay, thanks very much. Now,
it will just continue with the same schedule.
yeah, okay.
We'll continue with the same schedule, although we're running late, and we'll just pick up things from lunch a little bit later.
Okay.